Hello, this is Giacomo Indiveri from the University of Zurich and ETH Zurich at the Institute of Neuroinformatics. It's going to be a pleasure for me to give you a talk about brain-inspired strategies for low-power artificial intelligence computing systems. So the term artificial intelligence actually has become very, very popular in recent times. In fact, artificial intelligence algorithms and networks go back to the late 80s. And although the first successes of these networks were demonstrated in the 80s, only recently these algorithms and the computing systems started to outperform conventional approaches for solving problems. In fact, in the field of machine vision from 2009 on. In 2011, in fact, the first convolutional neural network trained using backpropagation achieved impressive results that made the whole field explode. And the reason for the success of this approach, really, even though, as I said, it was started many, many years ago, only recently we started to be able to follow this success because and achieve really impressive performance, because the technologies, the hardware technologies started to provide enough computing power for these networks to actually really perform well. In addition, there's been now the availability of large data sets that can be used to train such networks, which also were not there in the 80s. And finally, several tricks and hacks and improvements in the algorithms have been proposed to actually make these networks very robust and very performant. However, they do have some problems. Most of these algorithms require a large amount of resources in terms of memory and energy to be trained. And in fact, if we do an estimate and we try to see how much energy is required by all of the computational devices that are in the world to implement such neural networks, it is estimated that by 2025, the ICT industry will consume about 20% of the entire world's energy. This is clearly a problem which is not sustainable. The other reason for, or one of the main reasons for these networks to be extremely power hungry is because they are requiring large amounts of data and memory resources. And in particular, they require to move data from the memory to the computing and from the computing back to the memory. So typically memory is used in DRAM chips, and these DRAM are at least 1,500 times more costly than any compute operation, Mac operations in these CNN accelerators. So it's really not the fact that we're doing lots of computation, it's really the fact that we're moving bits back and forth that is burning all of this energy. The other problem is more fundamental. It's not only related to technology, it's related to the theory and these algorithms. These algorithms actually, as I said, are very, very powerful in terms of recognizing images and solving, but they are very narrow in the sense that they are very specialized to only a very specific domain. These networks are programmed to perform a limited set of tasks, and they operate within a predetermined and predefined range. They're not nearly as general purpose as animal brains are. So even though we do call it artificial intelligence, it's really different from natural intelligence, the type of intelligence that we see in animals and in humans. And the backbone of these artificial intelligence algorithms is the backpropagation algorithm. Or if we're looking at time series and sequences, the backpropagation through time, BPTT algorithm. This is really an algorithmic limitation, even though it can be used to solve very powerful problems. Trying to improve this BPTT by making incremental changes is probably not going to lead to breakthroughs in understanding how to go from artificial intelligence to natural intelligence. And the way the brain works is actually quite different from backpropagation through time. If you look at neuroscience and if you study real neurons and real synapses and the sort of computational principles of the brain, you will realize that there's a big difference. So this problem has been recognized by many communities, many agencies. There is, for example, a recent paper by John Shelf that shows how to go beyond these problems and try to improve performance of computation. And if we look at this particular path that basically tries to put together new architectures, new packaging systems with new memory devices and new theories, one of the most promising approaches is the one that is here listed as neuromorphic. So what is this neuromorphic? This is the sort of the bulk of this talk that I am going to show you what we can do at the University of Zurich, but also at the startup that comes out of the University of Zurich, SynSense, with this type of approach, which is, as I said, taking the best of the new materials and devices, new architectures, and new theories, and trying to go really beyond what we have today. So the term neuromorphic was actually invented or coined many, many years ago by Carver Mead in the late 80s, and is now being used to describe different things. There's at least 3 big communities that are using the term neuromorphic. The original one that goes back to Carver Mead was referring to the design of CMOS electronic circuits that were used to emulate the brain, basically as a basic research attempt to try to understand how the brain works by building circuits that are equivalent. So trying to really reproduce the physics. And because of that, these circuits were using subthreshold analog transistors for the neural dynamics in the computation and asynchronous digital logic for communicating spikes across chips, across cores. It was really fundamental research. The other big community that now started to use the term neuromorphic is the community building practical devices for solving practical problems. In that case, this community is building chips that can implement spiking neural network accelerators or simulators, not emulation, but really now at this point, it's more an exploratory approach. It's being used to try to understand what can be done with this approach of using digital circuits to simulate spiking neural networks. Finally, the last community, or another large community that has started to use the term neuromorphic, is the one that has been developing emerging memory technologies, looking at nanoscale devices to implement long-term non-volatile memories, or if you like, memoristive devices. So this community also started using the term neuromorphic because these devices, they can actually store a change in the conductance, which is very similar to the way the real synapses work, when that they actually change their conductance when they change their synaptic weight. And this allows them to build in-memory computing architectures that are also, as you will see, very similar to the way real biological neural networks work. And it can really create high-density arrays. So we can actually, by using analog circuits, the approach of simulating digital spiking neural networks, and by using in-memory computing technologies, the hope is that we create a new field, which I'm calling here neuromorphic intelligence, that will lead to the creation of compact, intelligent, brain-inspired devices. And really, to understand how to do these brain-inspired devices, it's important to look at the brain, to go back to Carver Mead's approach and really do fundamental research in studying biology and try to really get the best out of all of these communities of the devices, of the sort of the computing principles using simulations and machine learning approaches, but also of neuroscience and studying the brain. And so here I'd like to just to highlight the main differences that are there between simulated artificial neural networks and really the biological neural networks, those that are in the brain. In simulated artificial neural networks, as you probably know, there is a weighted sum of inputs. The inputs are all coming in a point neuron, which is basically just doing the sum or the integral of the inputs and multiplying all of them by a weight. So it's really characterized by a big weight multiplication or matrix multiplication operation. And then there is a nonlinearity, either a spiking nonlinearity if it's a spiking neural network, or a thresholding nonlinearity if it's an artificial neural network. In biology, the neurons are also integrating all of their synaptic inputs with different weights. So there is this analogy of weighted inputs, but it's all happening through the physics of the devices. So the physics is playing an important role for computation. The synapses are not just doing a multiplication, they're actually implementing some temporal operators, integrating, applying nonlinearities, dividing, summing. It's much more complicated than just a weighted sum of inputs. In addition, the neuron actually has an axon and it's sending its output through the axon using also basically an all or none event, a spike. through time, because the longer the axon, the longer it will take for the spike to travel and reach the destination. And depending on how thick the axon is, how much myelination there is, it will be slower or faster. So also here, the temporal dimension is really important. In summary, if we really want to see the big difference, is that artificial neural networks, the ones that are being simulated on computers and GPUs, are actually algorithms that simulate some basic properties of real neurons, whereas biological neural networks really use time, dynamics, and the physics of their computing elements to run the algorithm. Actually, in these networks, the structure of the architecture is the algorithm. There is no distinction between the hardware and the software. Everything is one. And understanding how to build these types of hardware architectures, wetware or hardware, using CMOS, using memristors, maybe even using alternative, DNA computing or other approaches, will hopefully and probably lead to much more efficient and powerful computing systems compared to the artificial neural networks. So if we want to understand how to do this, we really need to do a radical paradigm shift in computing. Standard computing architectures are basically based on the von Neumann system, where you have a CPU on one side and memory on the other. And as I said, transferring data back and forth from the CPU to the memory and back is actually what's burning all the power. Doing the computation inside the CPU is much, much more energy efficient and less costly than transferring the data. In brains, what's happening is that inside a neuron, there are synapses which store the value of the weight. So memory and computation are co-localized. There is no transfer of data back and forth. Everything is happening at the synapse, at the neuron. And there is many distributed synapses, many distributed neurons. So the memory and the computation are intertwined together in a distributed system. And this is really a big difference. So if we want to understand how to really save power, we have to look at how the brain does it. We have to use these brain-inspired strategies. And the main 3 points that I'd like you to remember is that we have to use basically parallel arrays of processing elements that have computation and memory co-localized. And this is radically different from time multiplexing a circuit here. For example, if we have one CPU, two CPUs, but even 64 CPUs to simulate thousands of neurons, we are time multiplexing the integration of the differential equations in these 64 CPUs. Here, if we look at how to do it following this brain-inspired strategies, if we want to emulate 1,000 neurons, we really have to have 1,000 different circuits that are laid out in the layout of the chip, of the wafer, and then run these through their physics, through the physics of the circuits, analog circuits, digital circuits, but they have to be many parallel circuits that operate in parallel with the memory and the computation co-localized. That's really the trick to save power. The other is, if we have analog circuits, we can use the physics of the circuits to carry out the computation. That really, instead of abstracting away some differential equations and integrating numerically the differential equation, we really use the physics of the device to carry out the computation. It's much more efficient in terms of power, latency, time, and area. And finally, the temporal domain is really important. The temporal dynamics of the system have to be well matched to the signals that we want to process. So if we want to have very low power systems, and for example, we want to process speech, we have to have elements in our computing substrate, in our brain-like computer, that have the same time constants. Speech, for example, phonemes have time constants of the order of 50 milliseconds. So we have to slow down silicon to have dynamics and time constants of the order of 50 milliseconds. So our chips will be firing and going at, hertz, or maybe hundreds of hertz, but definitely not at megahertz or gigahertz like our CPUs or our GPUs are doing. And by having parallel arrays of very slow elements, we can still get very fast computation. Even if we have slow elements, it doesn't mean that we don't have a very fast reactive system. It's because they're working in parallel, and so at some point there will always be one or two of these elements that are about to fire whenever the input arrives. And we can have microsecond, nanosecond reaction times, even though we have millisecond dynamics. And this is another key trick to remember if we want to understand how to do this radical paradigm shift. And at the University of Zurich, at ETH, at the Institute of Neuroinformatics, we've been building these types of systems for many, many years. And we are now also building these systems at our new startup at SynSense. The type of systems are shown here. Basically, we create arrays of neurons with analog circuits. These circuits, as I told you, are slow. They have slow temporal nonlinear dynamics. As I told you, they are massively parallel. We do massively parallel operations. All of the circuits work in parallel. The fact that they are analog actually brings this feature that is basically device mismatch. All the circuits are inhomogeneous. They are not equal, and this actually can be used as an advantage to carry out robust computation. It's counterintuitive, but I will show you that it's actually an advantage to have variability in your devices. And this actually is also very nice for people doing memoristic devices that are typically very, very variable. The other features are that they are adaptive. All of these circuits that we have negative feedback loops. They have learning, adaptation, plasticity. So the learning actually helps in creating robust computation through the noisy and variable elements. By construction, there are many of these working in parallel. Even if some of these stop working, the system is fault tolerant. You don't have to throw away the chip like you would with a standard processor. If one transistor breaks, probably performance will degrade smoothly, but at least the system will be fault tolerant. And because we use both the best of both worlds, analog circuits for the dynamics and digital circuits for the communication, we can program the routing tables and configure these networks. So we have flexibility in being able to program these dynamical systems like you would program a neural network on a CPU, on a computer. Of course, it's more complex. We still have to develop all the tools, and SynSense and other colleagues around the world are still busy developing the tools to program these dynamical systems. It's not nearly as well developed as, you know, having a Java or a C or a Python piece of code, but there is very promising work going on. And now the question always comes, why do you do it? If analog is noisy and inhomogeneous, why do you go through the effort of building these analog circuits? So let me just try to explain that. There are several advantages. If you think of having large networks in which you have many elements working in parallel, for example, these memoristic devices in a crossbar array, and you want to send data through them, these memoristic devices, if you use the physics, they use analog variables. So if you just send these variables in an asynchronous mode, you don't need to use a clock. So you can avoid using digital clock circuitry, which is actually extremely expensive in terms of area requirements in large complex chips and extremely power hungry. So avoiding clocks is something really, really useful. If we don't use digital, if we're staying analog all the way from the input to the output, we don't need to convert. We don't need to convert from digital to analog to run the physics of these memristors. And we don't need to convert back from analog to digital. And these ADCs and these DACs are actually very expensive in terms of size and power. So again, if we don't use them, we save in size and power. If we use transistors to do, for example, exponentials, we don't need to have a very complicated digital circuitry to do that. So again, we can use a single device that through the physics of the device can do complex nonlinear operation that saves area and power as well. And finally, if we have analog variables like variable voltage heights, variable voltage pulses, widths, and other types of variable currents, we can control the properties of the devices that we use, these memoristic devices. We can make them, depending on how strong we drive them, we can make them volatile or non-volatile. We can use their intrinsic nonlinearities. Depending on how strongly we drive them, we can even make them switch with a probability. So we can use their intrinsic stochasticity to do stochastic gradient descent, or to do probabilistic graphical networks, to do probabilistic computation. And we can also use them in their standard way of operation, in their non-volatile way of operation, as long-term memory elements. So we don't need to shift data back and forth from peripheral memory back. We can just store the value of the synapses directly in these memoristic devices. So if we use analog for our neurons and synapses in CMOS, we can then best benefit the use of future emerging memory technologies, reducing power consumption. And in a very recent, in the last ISCAS conference, which was just a few weeks ago, we did show with the PCM trace algorithm or the PCM trace experiments that we can exploit the drift of PCM devices, which are these shown here in a picture from IBM, to implement eligibility traces, which is a very useful feature to have for reinforcement learning. So if we are interested in building reinforcement learning algorithms, for example, for having behaving robots that run with brains that are implemented using these chips, we can actually take advantage of the properties of these PCM devices that are typically thought as non-idealities. We can use them to our advantage for computation. Now, analog circuits are noisy. I told you they are variable and inhomogeneous. For example, if you take one of our chips, you stimulate the neurons with the same current to all the neurons, to 256 different neurons, and you see how long it takes for the neuron to fire. Not only these neurons are slow, but they're also variable. The time at which they fire can greatly change depending on which circuit you're using. And there is this noise, which is typically you have variance of 20% over the mean. So the coefficient of variation is about 20%. So the question is, how can you do robust computation using this noisy computational substrate? And the obvious answer, the easiest thing that people do when they have noise, is to average. So we can do that. We can average over space and we can average over time. If we use populations of neurons, not single neurons, we can just take 2, 3, 4, 6, 8 neurons and look at the average time that it took for them to spike. Or if they're spiking periodically, we can look at the average firing rate. And then if we integrate over long periods of time, we can average over time. So these two strategies are going to be useful for reducing the effect of device mismatch if we do need to have precise computation. And we are doing experiments in these very days. This is actually a very recent experiment where we took these neurons and we put 2 of them together, 4 of them together, 8, 16. If you look at the cluster size, basically that's the number of neurons that we are using for the average over space. And then we are computing the firing rate over 2 milliseconds, 5 milliseconds, 50 milliseconds, 100, and so on. And then what we do is we calculate the coefficient of variation, basically how much device mismatch there is. The larger the coefficient of variation, the more noise. The smaller the coefficient of variation, the less noise. So we can go from a very large coefficient of variation of, say, 12, actually 18, as I said, 20%, by integrating over long periods of time or by integrating over large numbers of neurons, we can decrease this all the way to 0.9. And you can take this coefficient of variation and you can calculate the equivalent number of bits. If we were using digital circuits, how many bits would this correspond to? So by just integrating over larger number of neurons and over longer periods, we can have, for example, a sweet spot where we have 8-bit resolution just by using 16 neurons. And integrating, for example, over 50 milliseconds. This can be changed at runtime. If we want to have a very fast reaction time and a coarse idea of what the result is, we can have only 2 neurons and integrate only over 2 milliseconds. Then there's many false myths. When we use spiky neural networks, people tell us, oh, but if you have to wait until you integrate enough, it's going to be slow. If you have to average over time, it's going to take area. All of these are actually false myths that can be debunked by looking at neuroscience. Neuroscience has been studying how the brain works. The brain is extremely fast. It's extremely low power. We don't have to wait long periods of time to make a decision. So if you use populations of neurons to average out, it's been shown, for example, experimentally with real neurons, that populations of neurons have reaction times that can be even 50 times faster than single neurons. So by using populations, we can really speed up the computation. If we use populations of neurons, we don't need them to be, every neuron to be very highly accurate. They can be noisy and they can be very low precision, but by using populations and using sparse coding, we can have very accurate representation of data. And there is a lot of work, for example, by Sophie Deneuve that has been showing how to do this by training populations of neurons to do that. And now it should be also known in technology that if you have variability, it actually helps in transferring information across multiple layers. And here, what I'm showing here is data from one of our chips where we use 16 of these neurons per core, and we basically provide some desired target as the input. We drive a motor with a PID controller, and we minimize the error. It's just to show you that by using spikes, we can actually have very fast reaction times in robotic platforms using these types of chips that you saw in the previous slides. In fact, we've been building many chips for many years. Also at Sinsense, the colleagues are building chips. And the latest one that we have built at the university as a academic prototype is called the dynamic neuromorphic asynchronous processor. It was built using a very old technology, 180 nanometer, as I said, because it's an academic exercise. But still, this has 1,000 neurons. It has 4 cores of 256 neurons each. We can actually do very interesting edge computing applications just with a few hundred neurons. And then, of course, then the idea is to use both, the best of both worlds, to see where we can do analog circuits to really have low power, or digital circuits to have, to verify principles and make, practical problems, solve practical problems quickly. And then by combining analog and digital, we can also there get the best of both worlds. So to conclude, actually, I would just like to show you examples of applications that we built using this. This is a long list of applications, but if you have the slides, you can actually click on the references and you can get the paper. The ones highlighted in red are the ones that have been done by Sinsense, by our colleagues from Sinsense on ECG anomaly detection. And the detection of vibration anomalies was actually done by Sinsense and by University of Zurich in parallel independently. And just go to the last slide where I basically tell you that we are now at a point where we can actually use all of the knowledge from the university about brain-inspired strategies to develop this neuromorphic intelligence field, transfer all of this know-how into technology, and with new startups that can actually use this know-how to solve practical problems, and try to find, what is the best market for this. As I said, industrial monitoring, for example, for vibrations is something, but something that can also be done using both sensors and processors is really what the Sinsense company has been developing, and it's been really successful at, for doing intelligent machine vision, for putting both sensing and artificial intelligence algorithm on the same chip, and having a very low power in the order of microwatt, tens or hundreds of microwatt power dissipation for solving practical problems that can be useful in society, and in fact, even solving consumer applications. So with this, sorry, I went a bit over time, but I would just like to thank you for your attention